For astronomers, one seemingly quiet giant galaxy in a distant cluster hides a staggering secret. At its core lies the black hole in Abell 1201's brightest cluster galaxy, an ultra-massive object whose gravity is so strong it bends and magnifies the light of another galaxy far behind it. Today we explore the true scale of this black hole and where it sits among the most extreme objects in the universe. If you enjoy journeys into deep gravity like this, please subscribe and share, and tell us in the comments, how big do you think black holes can really get? Thank you for watching. Now let's begin. In the present universe, black holes appear across a wide span of masses and environments, and a scientific description of their scale begins with this census. A black hole is defined in general relativity as a region where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. The simplest way to organize the known population is by mass. At the lowest end of the firmly established range are stellar mass black holes formed from the collapse of massive stars when their nuclear fuel is exhausted. These objects typically have masses from a few times the mass of the Sun up to a few tens of times the mass of the Sun. They're found in binary star systems where gas from a companion star falls toward the black hole and heats to high temperatures, producing X-ray emission, and they're also detected through gravitational waves when two stellar mass black holes merge. Surveys of the Milky Way and nearby galaxies indicate that there are likely many stellar mass black holes for every large galaxy, although only a small fraction are currently detectable, because most do not have bright companions or ongoing accretion. Above this stellar range, astronomers have long discussed the possibility of intermediate mass black holes, with masses from a few hundred to perhaps hundreds of thousands of times the mass of the Sun. Evidence for these objects remains less secure than for other categories. Some dense star clusters show kinematic signatures that could be explained by an unseen central mass in this intermediate range, and a few ultraluminous X-ray sources in external galaxies have luminosities that might require such masses if they radiate near standard limits. However, the data can often be fitted by alternative explanations such as stellar mass black holes with beamed or supercritical accretion flows. As a result, the population of intermediate mass black holes is still under active study, and their exact abundance and role in galaxy evolution remain uncertain. At the high end of the mass spectrum are supermassive black holes which reside in the centers of galaxies. Their masses range from a few million to a few billion times the mass of the Sun. They are detected through multiple methods. In some nearby galaxies, including the Milky Way, high-resolution measurements of stellar orbits or gas motion in the central region provide direct dynamical evidence for a compact mass that cannot be explained by ordinary stars alone. In active galactic nuclei, where gas falls rapidly toward the central black hole, the broad emission lines from the gas respond to changes in the continuum light with a measurable delay. This reverberation mapping technique, combined with estimates of gas velocity, yields an estimate of the black hole mass. There are also rare megamaser systems where water molecules in a circumnuclear disk act as natural microwave lasers. Careful mapping of their orbits provides very precise mass measurements. Across all of these methods, a general pattern emerges. More massive galaxies tend to host more massive central black holes, and there are empirical relations linking black hole mass to properties such as the velocity dispersion of the surrounding stars and the total stellar mass of the bulge. At still higher masses in the most massive galaxies, particularly those found near the centers of galaxy clusters, evidence points to ultra-massive black holes with masses of many billions of times the mass of the Sun. These objects extend the supermassive category into a regime where the black hole mass becomes a significant fraction of the stellar mass contained in the inner region of the galaxy. Their presence is inferred from stellar kinematics on kiloparsec scales, from the structure of central light profiles, and in a few cases from gravitational lensing signatures that require an extreme central mass concentration. Mass estimates in this range carry larger uncertainties because they depend on detailed modelling of both the stars and the dark matter potential, and because the sphere of influence of such a black hole, although large compared with a typical galaxy nucleus, can still be difficult to resolve at the distances of massive clusters. Even so, multiple independent studies find that some central galaxies require black hole masses of several tens of billions of times the mass of the Sun to match the observations. Taken together, this census of black holes spans many orders of magnitude in mass, from the remnants of individual massive stars to compact objects whose mass rivals or exceeds that of the entire stellar content of a large galaxy's inner region. The smaller black holes are numerous and widespread, scattered through galactic disks and halos as relics of stellar evolution. The larger black holes are far less common and are closely associated with galactic centers, where long-term inflow of gas and the hierarchical assembly of galaxies over cosmic time provide the conditions for sustained growth. In clusters of galaxies where many large galaxies merge and interact, central galaxies can grow to exceptional sizes, and their central black holes can reach the ultramassive regime. The distribution of black hole masses across this full range sets the outermost context for any study that tries to place one particular object on the mass scale, because it defines both the typical values and the extremes that current observations support. Within this framework, the most massive central black holes occupy the upper end of the known range, and their inferred properties are constrained by the same basic principles of gravity and dynamics that govern their less massive counterparts, even though the environments in which they are found differ markedly from the stellar systems that host ordinary stellar mass remnants. In most massive galaxies, particularly those with prominent central bulges, a massive black hole sits at the geometric and dynamical center, and understanding these central black holes as parts of their host systems is a key step in describing their scale. Observations across many nearby galaxies show that these central objects are not isolated anomalies, but are closely linked to the properties of the surrounding stellar component. In galaxies with well-defined bulges, the mass of the central black hole correlates with the stellar velocity dispersion in the bulge, which is a measure of how fast stars move in random directions under the combined gravity of stars' gas and dark matter. This empirical relation, often called the black hole mass-velocity dispersion relation, indicates that more massive bulges with higher characteristic stellar speeds tend to host more massive black holes. There are also correlations between black hole mass and the total stellar mass of the bulge, and between black hole mass and the central concentration of starlight. Although the scatter in these relations is significant and different, samples and measurement methods can yield slightly different slopes and normalizations. The overall pattern is stable. Central black hole mass increases with the mass and dynamical depth of the host bulge. The presence of a central black hole also has a direct dynamical effect on the innermost stellar orbits. The radius within which the gravity of the black hole dominates over the average gravitational pull of the surrounding stars is called the sphere of influence. Inside this region, stellar motions become more strongly affected by the central point mass. For a given black hole mass and stellar velocity dispersion, the radius of this sphere of influence can be estimated, and high-resolution spectroscopy or integral field measurements can then test whether the observed rise in stellar velocities near the center matches the expected signature of a central black hole. In nearby galaxies where such measurements are possible, the observed kinematic profiles generally support the presence of compact central masses whose size and invisibility are consistent with black holes, rather than clusters of dark stellar remnants or other alternatives. These dynamical measurements, together with gas kinematics and massa observations in special cases, provide the foundation for the current mass scale of central black holes across the galaxy population. Central black holes also reveal themselves through accretion, the process in which gas spirals inward under gravity, releasing gravitational energy as radiation. When the inflow rate is high, the central region shines as an active galactic nucleus. In such systems, the luminosity of the nucleus can be a significant fraction of, or even exceed, the combined starlight of the host galaxy. The radiation field winds and sometimes relativistic jets emerging from the vicinity of the black hole interact with the surrounding interstellar medium. Over long time scales, these processes can heat expel or redistribute gas, potentially affecting the rate at which new stars form. Models of galaxy formation often include this feedback as a way to explain why the most massive galaxies today tend to have old stellar populations and little ongoing star formation. At the same time, not all central black holes are currently active. Many are in a low accretion state, producing only weak emission, or none that is detectable with current instruments. The history of their growth is reconstructed from the integrated light of past active phases and from the observed statistical distribution of active nuclei over cosmic time. The range of central black hole masses in galaxy cores extends from a few million times the mass of the Sun, as in the Milky Way, up to several billions of times the mass of the Sun in large elliptical galaxies. Within this range, the event horizon radius scales linearly with mass, so the physical size of the black hole grows in direct proportion to its mass. Even so, the event horizon remains extremely small compared with the overall size of the host galaxy. For a black hole with a mass of a few million solar masses, the event horizon radius is of order a few tens of microparsecs vastly smaller than the kiloparsec scale of a typical galactic bulge. For central black holes with masses of a few billion solar masses, the event horizon radius expands to a few tens of microparsecs, times the same factor still far below the spatial scales that can be resolved directly in all but the very nearest systems. Because of this disparity in scale, most of the evidence for central black holes comes from their gravitational influence on stars and gas at distances many thousands of times larger than the event horizon, and from the integrated emission of their accretion flows, rather than from direct imaging of the event horizon itself. Despite these observational limitations, the accumulated data support a coherent picture in which central black holes are standard components of massive galaxies. They grow over cosmic time through a combination of gas accretion and mergers with other black holes during galaxy mergers, and their final masses are tied in a statistical sense to the development of the galactic bulge. In disk-dominated galaxies with small bulges, central black holes tend to be less massive, while in massive elliptical galaxies with large dispersion, supported stellar components, central black holes tend to be more massive. The exact mechanisms that set these correlations are still an area of active research, but from the perspective of scale, the key point is that for any given galaxy, the central black hole mass is not arbitrary. It lies within a range that reflects the galaxy's overall mass and internal kinematics. This framework provides a reference against which especially massive central black holes in the most luminous galaxies can be compared. When a central galaxy in a dense environment appears to host a black hole whose inferred mass is far above the typical value expected for its stellar velocity, dispersion or luminosity, that object is flagged as an outlier in these relations and becomes a focus for detailed study. In galaxy clusters where the central galaxies are among the most massive known, and where multiple growth channels operate over long periods, some central black holes reach the upper extreme of the empirical mass distribution, extending the established patterns into the ultra-massive domain while still conforming to the same basic gravitational principles that govern smaller systems. On the largest gravitationally bound scales, known galaxy clusters occupy the dense nodes of the cosmic web and provide the environment in which some of the most massive central galaxies and their black holes are found. In the standard picture of structure formation, Small density fluctuations in the early universe grow over time as gravity pulls matter together. Dark matter collapses first into halos of many sizes, while gas follows and cools inside these halos to form galaxies. On very large scales, the matter distribution is not uniform but arranges into a network of low-density voids, sheet-like walls, elongated filaments, and dense intersections called nodes. Galaxy clusters sit at these nodes. They are built up over billions of years by the continuous infall of matter along filaments and by mergers between smaller groups and clusters. In this hierarchical picture present day, massive clusters are the endpoints of a long-growth history that involves both smooth accretion and discrete merger events. A typical rich galaxy cluster has a total mass of roughly a few hundred trillion to around 1 quadrillion times the mass of the Sun. Most of this mass is in dark matter, which forms an extended halo that dominates the cluster's gravitational potential. A smaller fraction is in the form of hot diffuse gas that fills the space between galaxies known as the intra-cluster medium. This gas is heated to tens of millions of degrees by the deep potential well of the dark matter halo and by shocks during structure formation, and it emits mainly in X-rays. Only a modest fraction of the cluster mass is locked up in stars distributed among hundreds to thousands of member galaxies, and in a diffuse intracluster-like component made of stars that have been stripped from their original host during tidal interactions and mergers. X-ray observations, gravitational lensing measurements, and galaxy dynamics all contribute to this picture of the cluster mass budget and confirm that dark matter and hot gas dominate the gravitational field on megaparsec scales. The spatial structure of a cluster reflects both its assembly history and its current dynamical state. In many systems, the overall mass and gas distributions are approximately symmetric and centrally concentrated, consistent with a relaxed configuration where the cluster has had time to settle into a quasi-equilibrium state after past mergers. In others, disturbed X-ray morphologies, irregular galaxy distributions, and features such as radio relics indicate ongoing merging activity or recent collisions between subclusters. Even in apparently relaxed systems, detailed studies often reveal substructure in the dark matter distribution and small offsets between the peak of the X-ray emitting gas and the centroid of the galaxy distribution. These features show that cluster formation is an ongoing process, and that complete dynamical relaxation is rare. However, on average, the central regions of massive clusters still provide deep, nearly stationary potential wells within which galaxies orbit and interact over long timescales. Within each cluster, galaxies are not distributed at random. There is usually a clear central concentration of galaxies, often dominated by one very luminous system near the bottom of the potential well. The galaxy population also varies with cluster-centric radius. The inner regions tend to be rich in early-type galaxies, with old stellar populations such as ellipticals and lenticulars, while star-forming disk galaxies are more common in the outskirts and in the filaments feeding the cluster. This environmental dependence of galaxy properties is interpreted as the result of processes such as ram pressure stripping by the intracluster medium tidal interactions and the cumulative effect of galaxy mergers, all of which are more effective in the dense central regions. Over time, repeated mergers and accretion of satellites build up a massive central galaxy. This object typically has an extended stellar envelope, a shallow surface brightness profile at large radii, and a luminosity that places it at the bright end of the galaxy population. From the perspective of central black hole growth, the cluster environment is important for several reasons. First, the deep cluster potential and the continuous supply of infalling galaxies favour the formation of a very massive central galaxy through cumulative mergers. Each merging galaxy can bring its own central black hole. When galaxies merge, their black holes sink toward the common centre through dynamical friction and can eventually coalesce, adding their masses. Second, the intracluster medium can provide gas to fuel accretion onto the central galaxy and its black hole, especially during phases when cooling of the hot gas overcomes heating processes. Third, the high density of galaxies in the core of a cluster increases the rate of tidal interactions and minor mergers, which further grow the central galaxy and help maintain a reservoir of gas and stars in its inner regions. These processes act over billions of years and can drive the central black hole toward the upper end of the known mass distribution. Clusters are also powerful gravitational lenses on large scales. The combined mass of dark matter gas and galaxies bends the paths of light from more distant background sources. When the alignment between the cluster and a distant galaxy is favorable, the background object can appear as an extended arc or as multiple images around the cluster center. The geometry and brightness of these lensed images provide direct constraints on the cluster mass distribution, independent of assumptions about the dynamical state of the system. Strong lensing regions typically trace the inner densest parts of the cluster potential, while weak lensing distortions of many background galaxies map the mass distribution out to large radii. Together with X-ray and dynamical data, these lensing measurements refine estimates of the cluster's total mass and concentration and reveal the contributions from individual massive galaxies in the core. In summary, at this stage, galaxy clusters are massive dark matter, dominated systems located at the nodes of the cosmic web, with sizes of a few million light-years and masses of hundreds of trillions of solar masses or more. They assemble over long timescales by accreting matter along filaments and by merging with smaller structures. Their cores contain dense concentrations of galaxies and hot gas, and their centers are usually occupied by a particularly luminous galaxy embedded in the deepest part of the gravitational potential. It is within these central regions of clusters where the matter density and merger history reach extreme values that the most massive central black holes are expected and observed to reside. In many galaxy clusters, one galaxy stands out as the most luminous and most massive member, and this object is called the brightest cluster galaxy. In most cases, it is an elliptical galaxy that lies very close to the minimum of the cluster gravitational potential and near the peak of the X-ray emission from the hot intracluster gas. Its stellar body is large and centrally concentrated, and in a significant fraction of systems, it is surrounded by an extended low-surface brightness envelope that blends into the diffuse intracluster light. When such an extended halo is present, the galaxy is often described as a CD galaxy, meaning an elliptical-like core embedded in a much larger stellar envelope that can reach radial scales of hundreds of thousands of light-years. Surface brightness profiles of brightest cluster galaxies are commonly described by Sersic or de Vaucouleurs laws, and in many cases a single such function does not fit all radii, so a double-component model is used with an inner profile representing the main galaxy and an outer component representing the extended envelope. Deep imaging shows that this envelope is not a simple smooth extension of the inner galaxy, but includes tidal features, shells, and asymmetries that record a long history of mergers and interactions. Measurements of the total luminosity and stellar mass indicate that brightest cluster galaxies typically have stellar masses of order a few trillion times the mass of the Sun, making them among the most massive stellar systems known. Their half-light radii are of order several tens of kiloparsecs or more, and when the extended halo is included, the detectable starlight can span scales comparable to a substantial fraction of the cluster core. In addition to their high mass, many brightest cluster galaxies show structural features such as boxy or disky isophotes, multiple nuclei or close companions projected onto their inner regions, all of which are consistent with formation through repeated mergers. The diffuse stellar envelope is closely related to the intracluster light, which consists of stars that are no longer bound to any single satellite galaxy, but orbit in the cluster potential. Observations and simulations both indicate that this component grows over time as galaxies are tidally stripped and disrupted, and that the inner part of the intracluster light overlaps with the outer halo of the brightest cluster galaxy. As a result, separating the galaxy from the cluster stellar component is partly a matter of definition and depends on the surface brightness limit of the data and on the choice of profile model used to fit the light. Kinematic studies provide complementary information about these systems. Spectroscopic measurements of stellar absorption lines show that the central velocity dispersions of brightest cluster galaxies are high, typically several hundred kilometers per second, reflecting both their large mass and the deep potential well at the cluster center. At larger radii, the stellar kinematics can show transitions from motions dominated by the central galaxy to motions that trace the cluster potential, and some studies find evidence for radial gradients in velocity dispersion or orbital anisotropy. These data, combined with surface brightness profiles, allow dynamical models that estimate the distribution of mass between stars and dark matter in and around the galaxy. The dark matter halo is extended and contributes significantly at large radii, while in the inner region the stellar mass density is high and can dominate the local gravitational field outside the sphere of influence of any central black hole. Formation scenarios for brightest cluster galaxies make use of both observational evidence and numerical simulations. In hierarchical models of structure formation, these galaxies grow through a combination of early major mergers and later minor mergers. Early in the cluster's history, when the universe is denser and gas-rich, major mergers between massive galaxies in the core can drive intense star formation and rapidly build a large central stellar system. At later times, as the cluster grows and the supply of massive infalling galaxies declines, growth proceeds mainly through the accretion of smaller satellites. Dynamical friction slows these satellites and causes them to sink toward the cluster center, where they can merge with the central galaxy, or be tidally disrupted and contribute their stars to the extended halo and intracluster light. The relative importance of in situ star formation versus accreted stars varies with redshift and environment, but by the present epoch, the central parts of brightest cluster galaxies are dominated by old stellar populations with little current star formation in many systems, while some hosts of cooling flows and clusters with short gas cooling times show residual star formation and emission line nebulae. Brightest cluster galaxies also often contain central radio sources associated with active galactic nuclei, powered by accretion onto their central black holes. These radio sources inflate cavities in the surrounding hot intracluster gas and heat it through mechanical work offsetting radiative cooling in many clusters. This feedback loop between the central galaxy, its black hole, and the intracluster medium is inferred from correlations between radio power, X-ray cavity energetics, and gas cooling properties. The persistence of old stellar populations in many brightest cluster galaxies and the suppression of large-scale cooling flows indicate that this feedback can be efficient over long timescales. From the point of view of internal structure, brightest cluster galaxies often show depleted stellar cores in their brightness profiles, where the central light falls below the inward extrapolation of the outer Circic profile. These cores are interpreted as the result of scouring by binary black holes formed during mergers which eject stars from the center through gravitational interactions. The sizes of these cores correlate with galaxy and black hole properties in samples where masses are measured dynamically. The combination of high stellar masses, high central velocity dispersions, extended envelopes, and evidence for core scouring all point to a formation history dominated by dry gas poor mergers and to central regions in which massive black holes are expected. Indeed, dynamical studies and analyses of radio and X-ray data for samples of brightest cluster galaxies indicate that many of them likely host central black holes with masses in the range of several billions to tens of billions of times the mass of the Sun, extending the scaling relations established for less massive ellipticals into the regime of ultramassive black holes, although with increased scatter and indications that some brightest cluster galaxies may lie above the average trends defined by the general galaxy population. The Abell 1201 cluster is a specific example of a rich galaxy cluster in the nearby universe, observed at a moderate redshift and studied in detail with both X-ray and optical data. It lies at a redshift of around 0.169, corresponding to a look-back time of roughly 2 billion years and a comoving distance of around 800 megaparsecs, or about 2.7 billion light-years. On the sky, it appears as a concentration of galaxies in the direction of the constellation Leo, with Abell 1201 BCG as its brightest member near the projected centre. In deep optical images, the cluster shows a dense core of galaxies surrounded by a more diffuse population extending over several arc-minutes, which corresponds to scales of order a few million light-years at the cluster redshift. The galaxies in the central region are predominantly early-type systems with smooth light profiles and red colours, typical of a mature cluster population in which most star formation has already ceased. Spectroscopic surveys identify several hundred member galaxies with velocities that cluster around the systemic redshift. The distribution of their line-of-sight velocities has a dispersion of several hundred kilometers per second, indicative of a deep gravitational potential, well with a total mass of at least a few hundred trillion times the mass of the Sun. The velocity distribution is close to Gaussian overall, which is consistent with a largely virialized system, but more detailed analysis reveals substructure in both position and velocity space, pointing to a complex assembly history. X-ray observations with observatories such as Chandra show that Abell 1201 contains a bright intracluster medium of hot gas that fills the space between the galaxies. The gas temperature is of order several keV, corresponding to tens of millions of degrees Celsius, and the X-ray surface brightness peaks near the cluster core. The X-ray morphology is not perfectly smooth. Instead, images reveal sharp surface brightness discontinuities known as cold fronts, where denser cooler gas comes into contact with hotter surrounding gas while maintaining approximate pressure balance. Temperature maps show that these fronts are associated with a cool core structure and with regions of hotter gas that likely trace shock heating or sloshing motions induced by past mergers. The presence of multiple cold fronts and a remnant core suggests that Abell 1201 has undergone at least one significant merger event with a smaller subcluster. In this interpretation, the remnant core of the infalling system has survived as a coherent structure and is now moving through the main cluster, displacing and perturbing the hot gas and creating the observed fronts. The galaxy distribution supports this picture. Density maps of confirmed members show localized overdensities and alignments that correspond to the positions of X-ray substructures. In particular, one overdensity is closely associated with the remnant X-ray core, and dynamical analysis indicate that this substructure is likely bound to the main cluster, rather than being an unassociated background or foreground group. Two-body models of the interaction suggest that the system is observed in a late stage of a merger after first core passage but before complete relaxation. Despite this dynamical activity, the overall gravitational potential remains centrally concentrated, and the cluster retains a dominant central region in which Abell 1201 BCG occupies a privileged position. Measurements of the X-ray emitting gas allow estimates of the cluster mass profile under the assumption of hydrostatic equilibrium, where the pressure gradient of the gas balances the gravitational pull of the total mass. These analyses, although affected by uncertainties related to deviations from perfect equilibrium in a disturbed system, indicate that Abell 1201 has a mass typical of a moderately rich Abell-class cluster, with a characteristic radius on the order of a few megaparsecs within which the mean density exceeds the cosmic critical density by a factor of several hundred. When combined with the galaxy dynamics, these X-ray based mass estimates suggest that dark matter dominates the total mass budget, with baryons contributing mainly through the hot gas and the stellar content of the cluster galaxies. The hot gas mass fraction within the characteristic radius is similar to that found in many other clusters and provides an additional consistency check on the mass scale. Optical imaging further reveals a population of intra-cluster stars that contribute to a diffuse light component spread over the inner region of the cluster. This intra-cluster light is most prominent around the central galaxy, but can be traced over scales larger than the main stellar body of any individual member. It provides evidence for ongoing tidal stripping and disruption of galaxies as they orbit in the cluster potential. The spatial distribution of this diffuse light follows the general shape of the central potential and overlaps with the region in which the X-ray surface brightness is highest, reinforcing the picture of a dense, dynamically active core. At the redshift of Abell 1201, the cluster is not among the most distant known, nor is it among the most massive extreme systems such as the hottest or most X-ray luminous clusters. Instead, it represents a massive cluster at intermediate redshift that combines relatively high mass with clear signatures of recent or ongoing dynamical activity in its core. Its properties place it within the broad family of cold front clusters, where the interplay between mergers gas dynamics and the central galaxy can be studied in detail using modern X-ray and optical facilities. In the inner region of the Abell 1201 cluster, the distribution of galaxies' hot gas and dark matter defines a central structure in which Abell 1201 BCG occupies a particular position relative to the main potential well and the surrounding intracluster medium. Maps of the projected galaxy density constructed from confirmed member galaxies show a strong concentration of galaxies around the brightest cluster galaxy, with additional overdensities marking substructures associated with the recent merger history. The central galaxy sits close to the peak of the galaxy surface density and near the kinematic center defined by the mean velocity of the cluster members, indicating that it traces the bottom of the overall gravitational potential when only the galaxy distribution is considered. However, X-ray images of the hot intracluster gas reveal a slightly different picture. The peak of the X-ray surface brightness, which corresponds roughly to the location of the densest, coolest gas, is offset by roughly 10 kiloparsecs from the center of Abell 1201 BCG. This offset is accompanied by two clear surface brightness discontinuities in the gas interpreted as cold fronts, where cooler, denser gas moves through a hotter ambient medium while remaining in approximate pressure balance. Temperature maps show that the gas in the vicinity of these fronts has a multi-phase structure with cooler regions embedded within hotter surroundings, and that the core gas appears to be sloshing within the cluster potential. The remnant core identified in the X-ray data sits near one of the galaxy overdensities, and moves relative to the main gas distribution consistent with a minor merger, in which a smaller subcluster has passed close to the center and displaced the cool core gas from the exact bottom of the potential. As a result, the center defined by the hot gas does not coincide perfectly with the center defined by the galaxy light, and the brightest cluster, galaxy, lies slightly downstream of the X-ray peak along the direction of motion inferred for the remnant core. The gravitational potential in the inner region is dominated by a combination of the dark matter halo, the stellar mass of the central galaxy, and the dense intracluster gas. Hydrostatic mass estimates using the X-ray emitting gas indicate that the mass profile rises steeply toward the center, as expected for a cluster with a cool core and a centrally concentrated dark matter distribution. At the same time, dynamical studies of the galaxy population reveal localized velocity substructures that match the positions of optical and X-ray features, confirming that the inner cluster is not perfectly relaxed. Two-body models treating the main cluster and the remnant core as interacting systems suggest that the merger is bound, and that the core is observed after at least one pericentric passage, a configuration that naturally produces the observed cold fronts and gas sloshing. Despite this dynamical complexity, the central region retains a clear, deep potential minimum that is closely associated with Abell 1201 BCG. Measurements of the intracluster light show that diffuse stars extend over scales comparable to the central few hundred kiloparsecs, and that their surface brightness peaks around the brightest cluster galaxy, blending into its extended stellar halo. This intracluster light traces stars that have been stripped from infalling galaxies and redistributed by tidal forces, and its concentration near the cluster center supports the view that the deepest part of the potential is centered on the bright galaxy and its surrounding dark matter. Radio observations detect an active radio source at the position of Abell 1201 BCG associated with an active galactic nucleus. Although the focus here remains on the cluster scale rather than the immediate nuclear region, the radio emission indicates that energy is being injected into the inner intracluster medium, and cavities or subtle disturbances in the gas may be linked to past outbursts. Together, the galaxy distribution X-ray morphology, temperature structure, and diffuse stellar component describe a central region in which the brightest cluster galaxy sits very close to the dynamical center defined by the total mass, while the cool core gas exhibits an offset and sloshing pattern that records the recent minor merger history of the system. Abell 1201 BCG is a massive elliptical galaxy located at the center of the Abell 1201 cluster and classified morphologically as an E3 type system with the characteristics of a CD galaxy. Its starlight distribution is extended and moderately flattened with an ellipticity of about 1/3, so the projected image on the sky is noticeably elongated rather than circular. Deep optical and near-infrared imaging shows that the galaxy has a high central surface brightness that declines gradually with radius, and that a single simple profile is not sufficient to describe the light at all radii. Instead, the inner region can be represented by a standard elliptical galaxy profile, while an additional outer component accounts for the extended low surface brightness halo that blends into the intracluster light. The effective radius, defined as the projected radius enclosing half of the total starlight, is about 15 kiloparsecs, which corresponds to several arc seconds at the redshift of the system. Within this radius, roughly half of the stellar mass of the galaxy is contained, while the rest is spread over larger radii, out to scales of order 100 kiloparsecs, where the surface brightness drops to very faint levels. The total stellar luminosity measured in optical and near-infrared bands is of order a few times 10 to the power of 11 times the solar luminosity in the optical, and more than 10 to the power of 12 times the solar luminosity in the near-infrared, placing Abell 1201 BCG among the most luminous known ellipticals. Photometric analyses fit the two-dimensional light distribution with elliptical isophotes, whose position angle is approximately constant with radius over the main body of the galaxy, indicating that the projected shape is coherent over a wide radial range. Small deviations from perfect ellipses are present in the form of isophote twists and boxy or disky distortions, but these are modest compared with some other brightest cluster galaxies, and are consistent with a predominantly relaxed stellar system that has nevertheless experienced mergers and tidal interactions. At very low surface brightness levels, images reveal features such as shells, faint streams or asymmetries that trace past accretion events, and the ongoing exchange of stars between the galaxy and the surrounding cluster potential. The stellar populations dominating the light in Abell 1201 BCG are old and metal-rich, as indicated by their red colours and spectral features measured in integrated light. Broadband colours and absorption line indices match those seen in other massive ellipticals with predominantly old stars that formed the bulk of their mass at early cosmic times and have experienced only limited subsequent star formation. Any young components, if present, contribute little to the total luminosity. As in other central cluster galaxies with extended envelopes, the transition between the inner galaxy and the surrounding diffuse stellar component is gradual rather than sharp. The surface brightness profile can be decomposed into an inner Cirsic-like component and an outer component that accounts for the intracluster light, but the exact division depends on the chosen fitting method and on the depth of the imaging data. In practice, observers define the galaxy extent by a combination of photometric thresholds and model fits, and quote sizes such as the effective radius and isophotral radii, at fixed surface brightness levels as standard descriptors. These size measures capture the fact that Abell 1201 BCG has a dense central body embedded in a much more extended stellar distribution that occupies a large fraction of the cluster core. The light profile also shows evidence for a mild central deficit relative to the inward extrapolation of the outer Cirsic component, a feature interpreted as a stellar core depleted by the action of binary black holes during past mergers. This central core has a size of order a few kiloparsecs and marks a region where the stellar density flattens compared with the steeper profile at larger radii. Outside this core, the surface brightness declines roughly as a smooth function of radius that can be well approximated by the chosen Cirsic law, plus envelope with no strong bar or disk structures. In projection on the sky, the main body of the galaxy spans a few tens of kiloparsecs along its major axis at intermediate surface brightness levels, while the extended halo and associated intracluster light can be traced to larger radii, limited by the sensitivity of the observations. Multiband imaging indicates only weak color gradients, with radius suggesting that the stellar population properties vary slowly across the main body of the galaxy, while any differences between the inner galaxy and the outer halo are subtle and require careful analysis. The orientation of the photometric major axis is broadly aligned with the distribution of nearby cluster galaxies and with a pattern of diffuse intracluster light, which is consistent with the central galaxy having grown through mergers along preferred directions set by the cluster potential. When compared with samples of brightest cluster galaxies in other systems, the sizes, luminosities and envelope properties of Abell 1201 BCG are typical of a very massive CD elliptical in a rich cluster with no prominent disk spiral arms or other late-type features, and with a smooth, slowly varying stellar light profile that reflects its status as a dominant early-type galaxy in a dense environment. Models that compare the observed colours and spectra with predicted populations of stars give a characteristic stellar mass-to-light ratio in the optical band that is high compared with less massive galaxies as expected for an old metal-rich population. Combining this ratio with the measured luminosity implies a total stellar mass of order, a few trillion times the mass of the Sun within the region where the light has been robustly measured. Although dynamical measurements are required to separate the contribution of dark matter from that of the stars, the photometric data alone already demonstrate that Abell 1201 BCG concentrates a very large amount of stellar material into a single elliptical system. Within the central tens of kiloparsecs, the smooth decline of surface brightness, the modest ellipticity variation with radius, and the absence of strong non-axis symmetric features indicate that the large-scale form of the galaxy is well described as a massive, slowly varying elliptical body with an extended halo dominating the luminous matter distribution in the core of the Abell 1201 cluster. The stars in Abell 1201 BCG move under the combined gravity of the stellar body, the surrounding dark matter, and any compact central mass and their motions provide direct information on how this mass is distributed within the inner few tens of kiloparsecs. To measure these motions, astronomers obtain spatially resolved spectra across the face of the galaxy using an integral field spectrograph, which records a full spectrum at each position in a two-dimensional field. In each spectrum, the absorption lines produced by the combined light of many stars are broadened and shifted by the range of line-of-sight velocities in that region. By comparing the observed line profiles with stellar templates, one can extract the mean velocity and the velocity dispersion, which is a measure of the spread of stellar speeds along the line of sight. In Abell 1201 BCG, the velocity field shows only weak large-scale rotation, and the random motions dominate as is typical for a massive elliptical galaxy. The main kinematic quantity of interest is therefore the velocity dispersion profile as a function of radius. Integral field data for this system show that within a projected radius of roughly 5 kiloparsecs, the line-of-sight velocity dispersion is close to constant at about 285 kilometers per second. Beyond this inner region, the dispersion does not decline, but instead increases steadily, with radius reaching values of around 360 kilometers per second at distances of order 20 to 30 kiloparsecs from the center. This behavior contrasts with that of many less massive early-type galaxies in the nearby universe, where the velocity dispersion profile tends to be flat or slowly falling with radius. In brightest cluster galaxies, rising profiles of this kind are more common, and are often interpreted as a signature of the growing influence of the cluster-scale dark matter, halo and intra-cluster light on the stellar motions at large radii. The shape of the dispersion profile in Abell 1201 BCG can be interpreted using dynamical models based on the Jeans equations, which relate the distribution of mass to the observed velocities in a collisionless stellar system. In such models, the observed surface brightness profile is deprojected to obtain a three-dimensional distribution of stars, and a parametrized mass model is adopted that includes contributions from the stars, an extended dark matter halo, and if required a compact central component. Anisotropy in the stellar orbits, meaning the relative weighting of radial and tangential motions, is also included through simple prescriptions. The model then predicts the line-of-sight velocity dispersion as a function of radius for given values of the mass components and anisotropy parameters. By adjusting these parameters to match the measured dispersion profile, one can infer which combinations of stellar mass dark matter and central compact mass are consistent with the data. For Abell 1201 BCG, such modelling shows that the rising dispersion at large radii cannot be reproduced if the mass follows the starlight alone with a constant stellar mass-to-light ratio. Instead, an extended mass component with a shallow density profile is needed, so that the enclosed mass continues to grow faster than the luminous matter alone as one moves outward. This requirement is naturally satisfied by including a dark matter halo of the type commonly inferred for massive galaxies and clusters, with a density that declines more slowly than the stellar density. The outer part of the observed dispersion profile is then explained by the increasing dominance of this halo over the stellar mass at radii of several tens of kiloparsecs. The observation that the dispersion continues to rise beyond the main body of the galaxy also indicates that the stellar motions there are already sensing the deeper potential well of the cluster, rather than only the self-gravity of the stellar component of the brightest cluster galaxy. In the inner few kiloparsecs, where the dispersion profile is nearly flat at a high value, the models indicate that an additional central concentration of mass is required to reproduce the data without invoking extreme orbital anisotropies. When only the stars and a standard dark halo are included, and a stellar mass-to-light ratio consistent with a normal initial mass function is assumed, the predicted dispersion in the central region is too low compared with the observations. Introducing a compact central mass added to the stellar distribution raises the inner dispersion and produces a better match to the measured profile, while still allowing a dark halo with a standard inner slope. The scale of this compact component inferred from the dynamical fits is of order a few tens of billions of times the mass of the Sun. Because the kinematic data used extend to radii of several kiloparsecs and cannot resolve scales close to any event horizon, the dynamical models are sensitive only to the total mass enclosed within these inner regions, not to its detailed distribution at very small radii. As a result, the compact central mass may represent a single massive object, such as a central black hole, or a combination of a central black hole and a region in which the stellar mass-to-light ratio is higher than average due to variations in the stellar population. Within the level of precision achievable with current data, both interpretations remain possible, and the dynamical analysis by itself does not uniquely distinguish between them. The same modelling also constrains the typical stellar mass-to-light ratio of the galaxy on kiloparsec scales. When a standard dark halo and a compact central component are both included, the best-fitting models for Abell 1201 BCG favour a stellar mass-to-light ratio compatible with a stellar population, similar to that inferred for massive ellipticals with a near Milky Way-like initial mass function, rather than requiring a systematically heavier distribution of low-mass stars. If the compact central mass is omitted from the models, the fits tend to shift toward higher stellar mass to light ratios and a dark matter halo, with a shallower inner density slope illustrating the degeneracy between these ingredients when the central mass is not accounted for explicitly. Including the compact mass leads to a solution in which the stars, the dark matter halo, and the central concentration each contribute in different radial ranges to the gravitational potential traced by the stellar motions. From the purely kinematic point of view, the key observational result is that Abell 1201 BCG has a high central velocity dispersion that remains nearly constant over the inner few kiloparsecs and then rises toward larger radii, and that this pattern can be reproduced by dynamical models only if the galaxy hosts both an extended dark halo and a substantial compact mass in its inner region, in addition to its already very massive stellar component. Within the central tens of kiloparsecs, the measured velocity dispersion at each radius therefore encodes the combined influence of these mass components on the gravitational field in which the stars of Abell 1201 BCG move. The mass distribution in and around Abell 1201 BCG includes not only the luminous stars but also a dominant dark matter halo that extends well beyond the visible extent of the galaxy and merges smoothly into the overall cluster-scale dark matter potential. In current models, this halo is described using parametrized density profiles that have been shown in simulations to approximate the equilibrium structure of collisionless dark matter halos formed by hierarchical clustering. A common choice is a profile in which the density decreases roughly as the inverse of radius in the inner region, and as the inverse cube of radius at large distances with a characteristic scale radius, where the logarithmic slope changes between these two regimes. The total mass within a given radius is then determined by the normalization of the profile, and by this scale radius, and the concentration of the halo is defined as the ratio between an outer reference radius, typically enclosing a mean density several hundred times the cosmic critical density in the scale radius. For a brightest cluster galaxy, such as Abell 1201 BCG embedded in the core of a massive galaxy cluster, the dark matter halo relevant for the inner tens of kiloparsecs is not a separate small halo, but the dense inner part of the larger cluster scale halo, possibly modified by baryonic contraction in response to the accumulation of baryons in the central galaxy. Dynamical models of Abell 1201 BCG that combine the observed stellar kinematics with reasonable assumptions about the dark matter distribution adopt halo parameters consistent with those predicted for halos of cluster mass in cosmological simulations, with scale radii of order a few hundred kiloparsecs and concentrations appropriate for the cluster's mass and redshift. Within the inner region, out to a few tens of kiloparsecs where the stellar kinematics and strong lensing constraints are available. The model predicts that the dark matter density declines more slowly with radius than the stellar mass density, so that even if the stars dominate the enclosed mass very close to the center, outside any compact central object, the fractional contribution of dark matter grows steadily with radius. At radii of several tens of kiloparsecs, dark matter and stars contribute comparably, and beyond this the dark component dominates. This behavior is reflected in the observed velocity dispersion profile, which rises at large radii as the stars begin to orbit more within the cluster scale potential than within the self-gravity of the stellar body alone. Gravitational lensing of a background galaxy by Abell 1201 BCG provides an independent probe of the projected mass distribution in the inner region. High-resolution imaging with the Hubble Space Telescope reveals a bright lensed arc at a projected radius of around 6 kiloparsecs from the galaxy center, produced by a background source at a higher redshift, whose light is deflected by the combined gravity of the stars and dark matter in the lens. Modelling of this arc with smooth mass distributions shows that a relatively high total mass is required within the Einstein radius, the characteristic radius of strong lensing where multiple images form. When this total mass is compared with what is expected from the stellar component alone using stellar population models to estimate the stellar mass to light ratio, it becomes evident that dark matter must already contribute significantly to the mass budget at this radius, even though the stellar density is still high. The lensing models therefore include both a baryonic component following the observed light and a dark matter halo with a shallower profile, and they adjust the relative contributions of these components to reproduce the detailed shape and position of the arc. The inclusion of dark matter is essential not only for matching the total enclosed mass, but also for obtaining a mass distribution whose angular structure follows the observed slight flattening and orientation of the stellar isophotes, while remaining consistent with the approximately elliptical global potential implied by the lens geometry. In some analyses, the dark matter halo is allowed to have a degree of ellipticity and a position angle relative to the line of sight so that the projected mass distribution is not simply circularly symmetric. For Abell 1201 BCG, combined lensing and dynamical models that explore such degrees of freedom find that reasonable fits to both the lensed arc and the stellar kinematics can be obtained with a halo whose flattening and orientation are broadly aligned with the observed stellar distribution. The mass enclosed within the Einstein radius is then partitioned between the stars which follow the light and the dark matter halo, whose density within this region is constrained by the requirement that the model reproduce both the lensing deflection angles and the velocity dispersion profile. These joint fits show that the dark matter fraction within the Einstein radius is non-negligible, and that extrapolating the stellar mass profile alone underestimates the total mass at that radius. As one moves outward to radii of several tens of kiloparsecs, the halo contribution grows, and in principle, weak lensing measurements of background galaxies beyond the bright arc could further refine the mass profile. Although for Abell 1201 the strongest current constraints in the inner region come from the single prominent arc and from the stellar dynamics, the presence of the cluster-scale dark matter halo also affects the interpretation of the innermost mass distribution. If the halo were to have a very shallow inner density slope approaching a constant density core, then more of the mass within the central few kiloparsecs would have to be supplied by the stars and any central compact object to explain the observed kinematics and lensing. Conversely, if the halo were more centrally concentrated than in standard models, with a steeper inner slope, it could account for a larger fraction of the central mass, reducing the amount that must be attributed to a compact object. The current analyses of Abell 1201 BCG typically adopt inner slopes consistent with standard cold dark matter halos, or allow modest deviations from them, and they explore how different assumptions about the halo profile change the inferred mass of any central black hole. In these studies, there is a degeneracy between the halo concentration and the compact mass models, with a highly concentrated halo can reduce the inferred black hole mass, while models with a halo closer to the average concentration for a cluster of this mass require a more massive compact object to match the same data. Within the plausible range of halo parameters supported by theory and by observations of other clusters, the dark matter halo in Abell 1201 BCG thus provides a smoothly varying background mass distribution, against which the more sharply peaked contributions of the stars and any central compact mass are superposed. Within the inner tens of kiloparsecs, the halo's role is to shape the overall depth and gradient of the potential, influencing the rising velocity dispersion profile and contributing substantially to the mass enclosed by the strong lensing region, while remaining less centrally concentrated than the luminous stellar component and any additional compact mass near the center. Gravitational lensing occurs when the gravity of a massive object such as a galaxy or cluster bends the path of light from a more distant source. In general relativity, mass curves space-time and light follows the curved paths, so that a background galaxy viewed through a massive foreground lens can appear distorted, magnified, or split into multiple images. When the alignment between source lens and observer is favorable, and the projected surface mass density of the lens exceeds a critical value, strong lensing takes place. In this regime, highly stretched tangential arcs and sometimes multiple distinct images form at characteristic radii that depend on the total mass enclosed in projection. The radius where these strongest distortions occur is often close to the Einstein radius of the lens, a scale that directly encodes the enclosed mass given the geometry of the system. Abell 1201 BCG provides a clear example of strong gravitational lensing on galactic scales within a cluster environment. High-resolution imaging with the Hubble Space Telescope first revealed a bright tangential arc located at a projected separation of roughly 2 arcseconds from the center of the brightest cluster galaxy, corresponding to a physical radius of about 6 kiloparsecs at the redshift of the system. Spectroscopy of this arc shows that it is a background galaxy at a redshift of about 0.451 behind the foreground cluster, at redshift about 0.169. The foreground galaxy and its surrounding dark matter halo deflect the light from the background source, producing an elongated image that wraps partly around the lens center and is oriented approximately tangentially with respect to that center. The arc is relatively short in angular extent compared with some cluster scale arcs, but its small projected radius means that it probes the projected mass distribution in a region where the stellar density of the brightest cluster galaxy is high and the contribution from dark matter is already significant, making it a sensitive constraint on the inner mass profile. To interpret the arc lens, models are constructed that combine a mass component following the observed stellar light of Abell 1201 BCG with an extended dark matter halo, and if needed an external shear term representing the tidal influence of the wider cluster potential. The stellar component is typically modelled using a mass distribution aligned with the observed isophotes, and scaled by a stellar mass to light ratio that is chosen within the range allowed by stellar population models. The dark matter halo is described by a smooth, centrally concentrated profile, with a shallower inner density slope than the stars, and an outer decline that matches expectations from cosmological simulations for cluster mass halos. The external shear term accounts for departures from circular symmetry, induced by mass outside the main lens galaxy, such as the rest of the cluster and neighbouring structures. For a given set of these components, ray tracing is used to map positions in the image plane back to positions in the source plane, and the shape, position and magnification of the lensed source are computed. The bright arc in Abell 1201 places tight constraints on these models. Its position at around 6 kiloparsecs fixes the projected mass enclosed within that radius to within a relatively small range, because the Einstein radius for the given source and lens redshifts is directly related to the total surface mass density at that radius. If the stellar mass distribution alone with a standard stellar mass to light ratio is used to represent the mass, the enclosed mass is too low to generate an Einstein radius as large as observed. Including a dark matter halo whose inner density slope and normalization are similar to those predicted for cluster cores increases the mass within 6 kiloparsecs to the required level. In this configuration, both stars and dark matter contribute significantly to the lensing mass, with the stars dominating the central surface density and the dark halo providing an extended background that maintains a high enclosed mass as radius increases. The precise division between stars and dark matter is adjusted so that the model reproduces the curvature length and distance from the lens center of the arc, as well as its orientation relative to the photometric axis of the galaxy. The morphology of the arc also requires that the projected mass distribution be moderately flattened and aligned in a way that is broadly consistent with the observed ellipticity and position angle of the brightest cluster galaxy, together with an external shear contribution from the cluster. Early analyses found that either a high ellipticity of the total projected mass or a substantial external shear was needed to reproduce the exact shape and location of the arc at such a small radius. Subsequent models that incorporate both an elliptical stellar mass distribution and an elliptical dark halo embedded in a cluster environment achieve good fits by sharing the flattening between the galaxy and the halo, and by including a shear term of plausible amplitude. These models yield a projected mass within the Einstein radius of roughly several 100 billion times the mass of the Sun, implying a projected mass to light ratio within 6 kiloparsecs that is higher than would be expected from the stellar population alone, but still compatible with a significant contribution from stars, plus a dark matter fraction of order tens of percent at that radius. Because the arc lies so close to the galaxy center in physical units, the strong lensing configuration of Abell 1201 BCG is unusual among cluster lenses. Many known cluster arcs form at tens of kiloparsecs from the central galaxy, where the cluster-scale dark matter halo dominates the lensing mass. In Abell 1201, the small Einstein radius means that the stars of the brightest cluster galaxy, the inner part of the cluster dark halo, and any additional central concentration of mass all contribute in comparable measure to the deflection of light that creates the arc. This makes the system particularly sensitive to the detailed inner mass profile, but it also introduces degeneracies between the contributions of the different components. Within the limits of current imaging data of the main arc, however, models that combine a luminous stellar mass distribution with a plausible dark matter, halo and cluster shear reproduce the observed arc without requiring extreme departures from standard assumptions about either the stellar population or the halo profile. In this sense, the bright tangential arc serves as a direct measurement of the total projected mass distribution in the inner few kiloparsecs of Abell 1201 BCG as encoded in the observed strong lensing pattern. Deep observations of Abell 1201 BCG reveal additional strong lensing features in its inner region that provide more stringent constraints on the central mass distribution than the bright tangential arc alone. Integral field spectroscopy with instruments such as the multi-unit spectroscopic explorer is used to isolate emission from the background source against the bright stellar continuum of the foreground galaxy. By constructing narrow band images around prominent nebular emission lines from the lensed source, such as doubly ionized oxygen, and subtracting the smooth continuum from the brightest cluster, galaxy observers enhance the visibility of any faint, spatially separate images of the background galaxy. In these data, a very low surface brightness feature is detected on the opposite side of the galaxy center, from the main arc, at a projected separation of about 0.6 arcseconds, corresponding to approximately 2 kiloparsecs at the cluster redshift. Spectra extracted at this location show the same emission line redshift as the main arc, confirming that this faint feature is a counter-image of the same background galaxy, rather than an unrelated object. Its geometry, with the bright arc on one side of the lens and the faint image on the other, and its location at a smaller radius, identify it as a central or inner image in the strong lensing configuration. In gravitational lensing theory, the existence, position, and brightness of central images are sensitive to the shape of the inner mass profile of the lens. For mass distributions that are approximately isothermal, meaning that the three-dimensional density falls roughly as the inverse square of radius in the inner region, the central image is highly demagnified and often lies so close to the center that it is effectively unobservable against the bright lens galaxy. If the inner density profile is shallower, approaching a constant density core, central images can be somewhat brighter and more easily separated from the center, while very steep inner profiles dominated by a point mass or a sharp central cusp can suppress or displace the central image. The detection in Abell 1201 BCG of a counterimage at a radius of order 2 kiloparsecs at a measurable but low flux relative to the main arc therefore provides specific information about the projected mass distribution in the innermost few kiloparsecs of the galaxy. Lens models constructed to reproduce both the bright tangential arc at around 6 kiloparsecs and this faint counterimage adopt a mass distribution composed at minimum of a component that traces the observed starlight of the brightest cluster galaxy and a dark matter halo with a standard form motivated by numerical simulations. When the stellar mass-to-light ratio is set to values consistent with stellar population models for an old metal-rich population, and the halo parameters are chosen within the range expected for a cluster core, these two components together can reproduce the position and curvature of the bright arc. However, in such standard two-component models, the predicted central image is either absent, extremely demagnified, or located much closer to the center than the observed counterimage. In other words, a mass model that explains the main arc under these assumptions does not naturally generate a detectable inner counterimage at the measured radius. To account for the observed counterimage modifications to the inner mass distribution are explored, one class of models preserves the standard form of the dark matter halo, but allows the stellar mass-to-light ratio to vary with radius increasing toward the center. In practice, this is implemented as a multiplicative gradient applied to the stellar mass component, so that the inner region within roughly 1 arcsecond has a higher mass-to-light ratio than the outer parts of the galaxy. Physically, such a gradient could correspond to a change in the stellar initial mass function, with the central region having a larger fraction of low-mass stars and stellar remnants than the outer galaxy. In Abell 1201, BCG lens models indicate that an increase in the stellar mass-to-light ratio by of order 60% inside the inner arcsecond is sufficient to produce a central image with the observed radius and brightness without greatly altering the fit to the main arc. This solution, however, requires a fairly strong radial variation in the stellar population properties and implies a very heavy initial mass function in the central region, significantly different from that inferred in many other massive ellipticals using independent spectral diagnostics. An alternative set of models introduces an explicit compact central mass component in addition to the stars and the dark halo. This component is treated as effectively point-like at the resolution of the lensing data and is naturally interpreted as a central supermassive black hole. When such a point mass is added at the galaxy center, its gravitational field steepens the total inner potential and modifies the critical curves of the lens. The main bright arc at 6 kiloparsecs remains well reproduced by adjusting the overall scaling of the stellar and dark matter components within the constraints already provided by the Einstein radius. The central image, however, shifts in radius and magnification in response to the point mass. By varying the mass of the central component, one can match the observed radius of the counter image at about 0.6 arc seconds and its flux relative to the main arc. For Abell 1201, BCG fits of this type favour a central mass of order 10 billion times the mass of the Sun, with uncertainties of several billion solar masses, depending on the detailed assumptions about the halo profile and external shear. This mass scale is comparable to the most massive black holes previously inferred in some brightest cluster galaxies through other methods, and is substantially larger than the value predicted by simple extrapolation of standard relations between black hole mass and host galaxy velocity dispersion. The two families of solutions, one invoking a strong radial gradient in the stellar mass to light ratio, and the other invoking a very massive central black hole, demonstrate that the inner lensing structure cannot be explained by stars and a standard halo alone, but they also highlight a degeneracy between different ways of concentrating mass in the centre. In models with a large central black hole, the stellar mass to light ratio can remain close to that expected for a near Milky Way-like initial mass function, and the dark halo can retain an inner slope consistent with the cuspy profiles seen in collisionless simulations. In models without a massive black hole, the required inward increase in stellar mass to light ratio implies a central stellar population that is substantially heavier than in the outer galaxy, and the dark halo contribution at small radii must be correspondingly reduced. Because both approaches can, within their respective parameter ranges, produce acceptable fits to the positions and relative magnifications of the bright arc, and the Countess image of the lensing data alone do not fully break this degeneracy. Subsequent imaging with the Hubble Space Telescope in blue filters, chosen to enhance the contrast between the blue star-forming background galaxy and the red stellar light of the foreground brightest cluster galaxy, improves the detection of the inner counter image and reveals its internal structure more clearly. These higher signal-to-noise data confirm the presence of a small radially extended lensed feature at around 1 kiloparsec from the galaxy center in projection, whose detailed morphology carries additional information about the gradient of the projected potential. When combined with more flexible lens models that allow the halo shape external shear and central point mass to vary, these data strengthen the case for a substantial compact mass component at the center, with inferred masses in the regime of several tens of billions of times the mass of the Sun when expressed with their full error ranges. At the same time, the models remain subject to systematic uncertainties associated with the choice of halo parametrization, the assumed stellar mass to light ratio, and its possible gradients, and the treatment of the cluster scale environment. Within the spatial region probed by the main arc and the inner counter image, the strong lensing configuration of Abell 1201 BCG therefore indicates that the projected mass distribution has a pronounced central concentration that cannot be captured by a simple combination of a constant mass to light stellar component and a standard dark matter halo. The existence and measured properties of the faint counter-image constrain the allowed shapes of the inner mass profile and require either an enhancement of stellar mass in the central kiloparsec or the presence of a very massive central compact object, with the current best-fitting models favouring a central mass in the ultramassive black hole range, while recognizing that degeneracies with the dark matter profile and stellar population remain. The combined analysis of lensing and stellar dynamics in Abell 1201 BCG is used to partition the central mass among stars' dark matter and a possible ultramassive black hole, and to quantify how model assumptions affect the inferred contribution of each component. In practice, this is done by constructing axisymmetric or spherical mass models that include 3 ingredients: a stellar mass distribution that follows the measured luminosity profile of the brightest cluster galaxy, a dark matter halo described by a parametrized density profile, motivated by numerical simulations of structure formation, and a central compact mass term representing a black hole. The stellar component is scaled by a stellar mass to light ratio, which is either taken as constant with radius or allowed to vary in some models, while the dark matter halo is specified by a characteristic density and scale radius that together define its mass and concentration on cluster scales. The black hole mass is treated as a free parameter within a broad prior range. For each choice of these parameters, the model predicts both the projected mass distribution, relevant for gravitational lensing, and the three-dimensional potential that determines the stellar velocity dispersion profile. These predictions are then compared with the observed positions and relative magnifications of the bright arc and inner counterimage, and with the spatially resolved stellar kinematics measured from integral field spectroscopy to identify combinations of parameters that are consistent with all available data. In models where the stellar mass-to-light ratio is constrained by stellar population synthesis to remain near values expected for an old metal-rich population with a near Milky Way-like initial mass function, the stars contribute a large but not dominant fraction of the mass within the Einstein radius of about 6 kiloparsecs. The dark matter halo provides a smoothly varying background that accounts for an increasing share of the enclosed mass beyond a few kiloparsecs, and is required to reproduce the rising velocity dispersion profile at large radii. Within this framework, lens models that include only stars and dark matter and omit a central black hole can match the bright tangential arc, but fail to produce the observed inner counterimage at its measured radius and brightness. When the stellar kinematics are added as constraints, such two-component models also struggle to fit the high central velocity dispersion without invoking extreme orbital anisotropies or an unusually shallow halo density slope. Allowing for a central compact mass in addition to stars and dark matter alleviates these tensions. As the mass of the central component is increased from zero, the predicted velocity dispersion in the innermost kiloparsecs rises, improving the match to the flat high dispersion observed there, while the position and demagnified flux of the central lensed image move toward the values measured in the spectroscopic and imaging data. The best fitting models in this family converge on central masses of order, several times 10 billion solar masses, with uncertainties of roughly a factor of 2, arising from allowable variations in the halo concentration external shear and the adopted stellar mass-to-light ratio. In representative solutions, the black hole mass is of order 3 times 10 to the power of 10 solar masses. The stellar component within a few kiloparsecs contributes a comparable or slightly smaller mass, and the dark matter halo contribution within the same region is significant but not dominant, rising to dominance only at larger radii. If the stellar mass-to-light ratio is instead allowed to increase sharply toward the centre, models can be constructed in which a smaller or even negligible black hole mass combined with a heavy central stellar population and a somewhat reduced dark matter density at small radii reproduces both the lensing configuration and the stellar kinematics. In these cases, the inferred stellar mass within the inner kiloparsec becomes very large, with implied central mass-to-light ratios that exceed those supported by independent spectral studies of similar galaxies, and the halo parameters must be adjusted to avoid over-predicting the total mass at the Einstein radius. The requirement of a strong radial gradient in the stellar mass-to-light ratio and the tension with external constraints on stellar initial mass functions in massive ellipticals lead many authors to regard this class of models as less natural than those with a substantial central black hole, although they cannot be ruled out solely on the basis of the lensing and dynamical data. In all of these models, there is a trade-off between the contributions of dark matter and the black hole in the central few kiloparsecs. If the halo is assumed to have an inner density slope shallower than the standard cuspiform, more of the central mass can be attributed to stars, and the black hole without exceeding the total mass allowed by lensing at 6 kiloparsecs. If the halo is taken to be more concentrated with a steeper inner profile, the dark matter fraction within the Einstein radius rises, and the required black hole mass decreases. Studies of Abell 1201 BCG typically constrain the halo concentration using relations between halo mass and concentration from cosmological simulations and from weak lensing observations of clusters, and they propagate plausible ranges of these values into the uncertainty on the black hole mass. Within these ranges, the inferred black hole mass remains in the ultramassive regime of at least several tens of billions of solar masses, when a constant or mildly varying stellar mass-to-light ratio is adopted. The stellar kinematics provide an important independent check on these allocations. Models that fit the lensing but assign too much mass to dark matter at small radii tend to predict a velocity dispersion profile that does not match the observed flat inner region and rising outer region simultaneously. By contrast, models that include a massive black hole, a stellar component with a standard or mildly enhanced mass to light ratio, and a dark halo of reasonable concentration can reproduce both the central and outer parts of the dispersion curve. In this joint lensing plus dynamical analysis, the mass budget inside the inner few kiloparsecs of Abell 1201 BCG is therefore divided among the three components in a way that depends on the adopted priors but consistently points to the need for a strong central mass concentration beyond the stars and standard halo. The numerical values assigned to each component vary across studies, but the qualitative picture that emerges is that the brightest cluster galaxy contains a very large stellar mass embedded in a cluster-scale dark matter halo, and in the central kiloparsec, an additional compact mass in the ultramassive range is strongly favoured when conservative assumptions about the stellar population and halo structure are used to interpret the combined lensing and dynamical data. When the compact central mass inferred in Abell 1201 BCG is interpreted as a black hole, its estimated mass places it in the ultramassive regime far above the range usually encountered in nearby galaxies. Lensing models that reproduce both the bright tangential arc at around 6 kiloparsecs and the inner counterimage at around 2 kiloparsecs, while keeping the stellar mass-to-light ratio and the dark matter halo within standard bounds, yield central masses of order, several tens of billions of times the mass of the Sun. Earlier joint analyses of lensing and stellar dynamics that allowed for a central point mass in addition to stars and a standard dark halo recovered a preferred mass of roughly 10 billion solar masses, with uncertainties of order a few billion, while more recent strong lensing reconstructions that use higher quality space-based imaging and explore a wider range of lens models favour a mass closer to 30 billion solar masses, with an uncertainty large enough that values between about 10 billion and a little more than 50 billion remain acceptable. The exact best-fitting value depends on the adopted form of the dark matter profile, the amplitude of the external shear from the cluster, and any priors on the stellar mass-to-light ratio. But across these studies, the central mass consistently lies well above the usual supermassive range of a few billion solar masses and firmly within what is commonly termed the ultramassive regime. In this interpretation, Abell 1201 BCG hosts a dormant ultramassive black hole, meaning that its central black hole is not presently in a strongly accreting, optically bright quasar phase, but is instead detected through its gravitational influence on stars and on the lensed background galaxy. The galaxy does contain a radio source at its centre, and the associated active nucleus injects energy into the surrounding hot intracluster gas, but the luminosity of this activity is modest compared with the most powerful quasars, and it does not by itself provide a reliable measure of the black hole mass. Instead, the mass estimate comes from fitting the detailed shape and position of the lensed images, and from matching the stellar velocity dispersion profile, both of which respond to the total gravitational field in the central few kiloparsecs. In these models, the black hole is treated as a point mass because its event horizon and immediate surroundings are tiny compared with the spatial resolution of the data, so the only relevant property of the black hole on these scales is its total mass. The inferred mass can be compared with empirical relations between black hole mass and host galaxy properties that have been established in nearby galaxies using stellar and gas dynamics. For galaxies with central stellar velocity dispersions of a few hundred kilometers per second, these relations typically predict black hole masses of a few hundred million to perhaps 1 or 2 billion solar masses. Abell 1201 BCG has a central velocity dispersion of roughly a few hundred kilometers per second within the inner several kiloparsecs and a total stellar mass of order a few trillion solar masses, values that would place it among the more massive ellipticals used to calibrate these relations. For such a host, the standard relations would suggest a central black hole mass of at most a few billion solar masses. The ultramassive values inferred from lensing and dynamics are larger by a factor of several to around an order of magnitude, indicating that if the compact mass is indeed a black hole, it is substantially more massive than the average object expected for a galaxy of this type. The result echoes other cases in which brightest cluster galaxies appear to host unusually massive black holes compared with the general population, but Abell 1201 BCG is distinctive in that its mass estimate comes primarily from strong lensing geometry rather than from spatially resolved stellar or gas dynamics alone. The radius within which the gravity of a black hole of this mass dominates over the combined gravitational pull of the surrounding stars is also large on galactic scales. Using a characteristic stellar velocity dispersion of a few hundred kilometers per second, the radius of influence defined as the radius where the enclosed stellar mass equals the black hole mass is of order a kiloparsec for a black hole of several tens of billions of solar masses. This distance is small compared with the full extent of the galaxy, which has an effective radius of about 15 kiloparsecs and a detectable stellar halo that extends to tens of kiloparsecs, but it is large compared with the radii of influence of more typical supermassive black holes in less massive galaxies, which are often only a few tens of parsecs. In Abell 1201 BCG, the sphere of influence therefore covers a sizable fraction of the inner region probed by the stellar kinematics, and part of the region where the strong lensing constraints are most sensitive, explaining why the presence or absence of a massive central object has a noticeable effect on both the velocity dispersion profile and the structure of the lensed images. The growth history required to reach such a mass is not directly constrained by the present data, but plausible channels can be outlined in broad terms. In the hierarchical picture of galaxy and cluster formation, the brightest cluster galaxy grows through repeated mergers with other massive galaxies over many billions of years. Each of these merging galaxies may bring its own central black hole, and successive black hole mergers can steadily increase the mass of the central object. Periods of rapid gas accretion during and after major mergers can further add to the mass, especially at earlier cosmic times when cold gas was more abundant in massive halos. Feedback from accretion in the form of radiation winds and jets interacts with the surrounding gas, and may regulate both the growth of the black hole and the star formation in the host galaxy. By the present epoch, the black hole in Abell 1201 BCG appears to have reached a state where its mass is very large while its current accretion rate is low, leading to a relatively faint nucleus compared with luminous quasars, even though the central mass is comparable to or larger than the masses inferred for the engines of some bright active galactic nuclei. Despite the uncertainties that remain in the exact decomposition of the central mass between the black hole, the stars and the dark matter halo, the characterization of the compact central component in Abell 1201 BCG as an ultramassive black hole is supported by the scale of the mass required by combined lensing and dynamical models under conservative assumptions about the stellar population and halo structure. Within the inner kiloparsec, the gravitational field is dominated by this compact mass, with the surrounding dense stellar body and the inner dark halo providing additional contributions that become more important at larger radii. On the scale of the galaxy as a whole, the black hole mass remains only a small fraction of the total stellar and dark matter mass. But in the central region it defines the depth and shape of the potential well in which the innermost stars and the strongly lensed images of the background galaxy orbit and form. Inside the central region of Abell 1201 BCG on scales of order, a kiloparsec and below the gravitational field becomes increasingly dominated by the compact central mass, inferred from the combined lensing and dynamical analyses, and the structure of the galaxy there reflects the interaction between this mass and the surrounding stellar body. The surface brightness profile shows a central core in which the stellar light is shallower than would be expected from the inward extrapolation of the outer Circic-like profile. This light deficit extends over radii of order a few kiloparsecs, and is a feature commonly found in the most massive elliptical galaxies and brightest cluster galaxies. In theoretical models, such depleted cores are produced when binary black holes formed during galaxy mergers eject stars from the center through repeated gravitational encounters, carving out a region where the stellar density is reduced relative to what it would have been in the absence of such a binary. The large size of the core in Abell 1201 BCG is therefore consistent with a history in which a very massive central black hole has grown through multiple mergers with other black holes delivered by infalling galaxies, each episode contributing to the expansion of the core as stars are scattered to larger radii or unbound from the galaxy. The mass associated with this light deficit is typically comparable to several times the black hole mass in empirical studies of core galaxies, so for an ultramassive black hole of several tens of billions of solar masses, the total stellar mass that has been displaced from the center can be very large, helping to explain the observed shallow central profile. On scales smaller than the core radius, but still much larger than the event horizon, the dominant luminous component is a dense pressure-supported stellar population with high-velocity dispersion. The stars in this region move on orbits that respond both to the overall potential of the galaxy and cluster, and to the steep inner potential generated by the compact central mass. Within the radius of influence of the black hole, which for the masses inferred in Abell 1201 BCG is of order a kiloparsec for the measured stellar velocity dispersion, the gravitational pull of the black hole contributes significantly to the acceleration of stars. In simple dynamical models, this influence is reflected in a flattening or upturn of the central velocity dispersion profile, and in subtle changes to the shape of the line-of-sight velocity distribution, which can become more peaked or more extended in the wings, depending on the mix of radial and tangential orbits. The integral field spectroscopy of Abell 1201 BCG shows a high, nearly constant dispersion in the inner few kiloparsecs and models that include a massive central point-like component reproduce this behavior without invoking extreme anisotropy, consistent with a region in which the random motions of stars are boosted by the strong central potential. Gas in the immediate surroundings of the black hole is present in much smaller quantities than the stars, but plays an important role in connecting the central object to the intracluster medium. X-ray observations of Abell 1201 reveal a cool core structure and cold fronts in the hot gas on scales of tens of kiloparsecs, indicating that gas is cooling and sloshing in the cluster potential. Some fraction of this gas can reach the central galaxy and provide a reservoir for low-level accretion onto the black hole. Radio observations show that the brightest cluster galaxy hosts a radio source, signaling the presence of an active galactic nucleus powered by accretion, although at a relatively modest level compared with luminous quasars. In many cool core clusters, such radio mode feedback manifests as jets and lobes that inflate cavities in the hot gas and heat the surrounding medium. While detailed radio and X-ray imaging of Abell 1201 is less extensive than for some nearby systems, the presence of a central radio source embedded in a cool core environment suggests that similar processes operate here with the ultra-massive black hole, driving episodic outbursts that regulate the thermodynamic state of the intracluster gas without requiring a high radiative output. On the spatial scales considered in this section of order are kiloparsec. The energy input from such activity acts mainly on the surrounding gas rather than directly on the bulk stellar component, but over long time scales, it influences the availability of cold gas for star formation in the central galaxy and the level of accretion onto the black hole itself. Within the central kiloparsec, any cold gas that survives or condenses out of the hot phase can settle into disks or filaments under the combined influence of gravity rotation and feedback from the active nucleus. In some brightest cluster galaxies, optical emission line nebulae and molecular gas structures are observed on these scales, tracing material that has cooled out of the intracluster medium and is being shaped by jets and radiation from the center. For Abell 1201, BCG existing observations focus primarily on the stellar kinematics and lensing signatures, and provide less direct information on cold gas morphology, but the general picture in similar systems suggests that if cold gas is present, it would occupy only a small fraction of the volume inside the sphere of influence, and would likely be confined to thin structures that are susceptible to disruption by feedback. In such an environment, star formation within the central kiloparsec is typically weak or absent, consistent with the predominantly old red stellar population inferred from the galaxy's integrated spectrum and colours. As the radius decreases further toward the black hole, the gravitational potential becomes increasingly dominated by the compact mass and the motions of any gas or stars that pass close to the centre, transition to orbits that are strongly influenced by the black hole alone. The region where relativistic effects become important for particle orbits lies far inside the spatial resolution of current observations of Abell 1201 BCG, so the structure there is not measured directly. Instead, models treat the black hole as a point mass and calculate its effect on observables at larger radii. In this framework, the central region accessible to observation consists of the depleted stellar core, the high dispersion inner stellar body, and any gas associated with the low luminosity active nucleus and its interaction with the intracluster medium. Together, these components trace a gravitational field in which the ultramassive central mass plays a leading role on kiloparsec scales, even though the event horizon itself remains unresolved. The kinematically hot old stellar population provides the main luminous tracer of this field, while the hot and possibly multi-phase gas records the ongoing exchange of energy between the black hole and its environment. Within this inner region, the mass distribution is therefore characterized by a steeply rising central contribution from the compact object embedded in a dense but partially depleted stellar background, all contained inside the broader, more slowly varying potential of the dark matter halo in the cluster core. For a compact central mass interpreted as a black hole, the most direct way to describe its physical scale is through the size of its event horizon, a boundary defined in general relativity as the radius at which the escape speed equals the speed of light. In the simplest non-rotating case, this radius, often called the Schwarzschild radius, is proportional to the mass of the black hole. For a mass equal to that of the Sun, the Schwarzschild radius is about 3 kilometers. For a black hole with a mass many times larger, the radius scales in direct proportion, doubling the mass. Doubles the radius increasing the mass by a factor of 10 increases the radius by the same factor, and so on. This linear scaling allows the characteristic size of black holes with very different masses to be compared using the same basic formula, even though their environments and formation histories differ. In Abell 1201, BCG combined strong lensing and dynamical models favour a compact central mass of about several tens of billions of times the mass of the Sun when interpreted as a black hole. Taking a representative value of around 30 billion solar masses, the corresponding Schwarzschild radius is obtained by multiplying the 3-kilometre radius for one solar mass by the same factor of 30 billion. This gives a radius of order 100 billion kilometres. The event horizon diameter twice this radius would therefore be of order 200 billion kilometres. These numbers are approximate because the black hole mass has uncertainties of roughly a factor of a few, and because the real black hole may rotate, which changes the exact horizon structure compared with the non-rotating case. But for the purpose of scale and event, horizon radius of about 100 billion kilometres is a useful reference. The same scaling applied to well-studied nearby supermassive black holes gives much smaller radii. Sagittarius A star. The black hole at the centre of the Milky Way has a mass of about 4 million times the mass of the Sun, as inferred from the orbits of stars that move around it in periods of a few years to a few decades. For that mass, the Schwarzschild radius is roughly 12 million kilometres, and the event horizon diameter is roughly 24 million kilometres, consistent with the size of the dark region and surrounding ring of emission measured by very long baseline interferometry. The black hole in the galaxy Messier 87, directly imaged by the Event Horizon Telescope, has a mass of about 6.5 billion solar masses. For that mass, the Schwarzschild radius is around 20 billion kilometres, and the diameter is about 40 billion kilometres, in agreement with estimates that the dark central region is roughly several tens of billions of kilometres across when interpreted as a projection of the black hole shadow. In both of these cases, the event horizon scale is tiny compared with the host galaxy, but the differences between the Milky Way Messier 87 and Abell 1201 BCG are large when expressed in absolute units. Comparing these three systems directly, a 30 billion solar mass black hole in Abell 1201 BCG has a Schwarzschild radius roughly 7,000 times larger than that of Sagittarius A star because its mass is larger by the same factor. It is also larger by a factor of about 5 than the event horizon radius of the black hole in Messier 87, because 30 billion solar masses is several times greater than 6.5 billion solar masses. In physical units, an event horizon radius of order 100 billion kilometres is about 3 times larger than the radius inferred for the black hole in Messier 87, and about 10,000 times larger than the radius for Sagittarius A star. The diameter of the event horizon in Abell 1201 BCG, around 200 billion kilometres in this scaling, can be related to familiar solar system distances for additional context. The average distance between Earth and the Sun is about 150 million kilometres. A diameter of 200 billion kilometres is therefore roughly 1,300 times that distance. Neptune orbits the Sun at a distance of about 4.5 billion kilometres, so the event horizon diameter would be comparable to around 40 times the radius of Neptune's orbit. Even with these large multiples of solar system scales, the horizon remains extremely small compared with the full size of the host galaxy. Abell 1201 BCG has an effective radius of about 15 kiloparsecs, which corresponds to roughly 50,000 light-years, and its extended stellar halo plus intra-cluster light reach to tens or even hundreds of kiloparsecs in projection. A light-year is about 10 trillion kilometres, so the main stellar body of the galaxy spans distances vastly greater than the 100 billion kilometre radius of the event horizon. In linear terms, the Schwarzschild radius of the black hole is a minute fraction of the effective radius of the galaxy, far less than 1% even when expressed as a ratio of radii rather than volumes. On cluster scales, the contrast is even larger. The characteristic radius within which the mean density of Abell 1201 exceeds the background density by several hundred is of order a few megaparsecs or a few million light-years, and the event horizon radius is negligible by comparison. Thus, while the black hole in Abell 1201 BCG is ultra-massive in terms of the amount of mass contained within its horizon, the spatial domain in which the horizon itself is relevant remains confined to the innermost microscopic part of the cluster when viewed in linear dimensions. The mass of the black hole can also be compared with the stellar mass of its host galaxy. Photometric and dynamical estimates place the total stellar mass of Abell 1201 BCG at of order a few trillion times the mass of the Sun within the radii, where the surface brightness can be measured reliably. A black hole mass of several tens of billions of solar masses is therefore a few percent of the total stellar mass of the galaxy. This ratio is higher than the typical fraction of about 0.1% to 1% inferred for many less massive early-type galaxies, but it remains small enough that the stars and dark matter dominate the mass budget on kiloparsec and larger scales. The event horizon scale reflects only the mass contained in the compact central object itself. Beyond the horizon, the gravitational influence of the black hole extends out to its sphere of influence, which for masses of several tens of billions of solar masses and stellar velocity dispersions of a few hundred kilometers per second is of order a kiloparsec. This sphere of influence defines the region where the enclosed stellar mass becomes comparable to the black hole mass, and where the orbits of stars and the structure of strong lensing images are most sensitive to the central mass. Outside this region, the gravitational field gradually transitions to one dominated by the combined mass of stars and dark matter, and the detailed properties of the event horizon become unimportant for the bulk dynamics of the galaxy. In summary of the purely geometric quantities considered here, treating the compact central mass in Abell 1201 BCG as a black hole implies an event horizon with a radius of about 100 billion kilometers and a diameter of about 200 billion kilometers for a representative mass of around 30 billion solar masses. This horizon is several thousand times larger in radius than that of Sagittarius A star, a few times larger than that of the black hole in Messier 87, and still extremely small compared with the half-light radius of the host galaxy and the characteristic radii of the Abell 1201 cluster. The event horizon scale thus encapsulates the extreme compactness of the central mass, while remaining consistent with the broader picture in which the majority of the mass in the galaxy and cluster is distributed over kiloparsec to megaparsec scales in stars, gas, and dark matter.